And we are going to be on page 8. Page 8. Yeah. This is so weird. Hi. Oh, which what? Who?
That's do you have an extra book for this unit?
They would be on the back thing there. And I think we do. Find one? Excellent. Okay, shielding an effective nuclear charge. So shielding an effective nuclear charge basically explain almost all of the periodic properties because both of these contribute in one way or another to the Coulombic attraction. And most often we're looking at how those two things, the shielding and the effective nuclear charge, affects the valence electrons. So they affect the Coulombic attraction on the valence electrons. And the Coulombic attraction accounts for all the periodic properties. So basically you need to know that negative electrons attract the positive protons, so they move closer together, and negative electrons repel other negative electrons. So there is repulsion. So we have attraction and we have repulsion. So let's take a look here at lithium. Okay, lithium is atomic number 3. And so that means it has how many protons? 3. And how many electrons? 3. 2 in its first shell and 1 in its second shell. Okay, so this is just laying it out. We have 3 protons. We have 2 core electrons. Although I don't know why I'm writing it there because guess what? Over here, it shows that we have 1 valence electron and 2 core electrons. So the 1s2 are our core and the 2s1 is our valence. So far, so good? Okay. We are going to show the attractive force of each proton with an inward pointing arrow. Okay, so each proton is pulling inwards, and that is the pulling force on the valence electrons. Okay, so these are the pulling force on the valence electron. we also have a repulsive force of the core electrons. So these push outward on the valence electrons. So in chemistry, we refer to the number of protons is Z, okay, which is also the nuclear charge. And if we think about Coulomb's law, do you guys remember Coulomb's law? Coulombic force is equal to KQ1 Q2 over R squared. Or if you prefer, you can say that the Coulombic force is proportional to Q, Q, Q1, Q2 over R squared. We're going to be doing some comparisons of the Coulombic force on an electron, on a valence electron between one type of atom and a different type of atom. So in this case, Q2 is going to be the same for both of these because it is the charge of the valence electron. Yeah? So any electron just has a charge of 1. So we can basically ignore Q2 because it's always going to be the same, because we're always saying, what's the force on this valence electron? What's the force on that valence electron? Does that make sense? So Q2 is always going to be 1, so we can just kind of ignore it because it won't be changing. Okay? So Q2, where can I write that? Q2, charge of valence electron does not change. Well, what the heck is Q1? Because we're always looking at one charge interacting with a second charge. So we're like, okay, Q2 is our electron. But we have so many protons here and so many electrons. Wouldn't it be nice if we could simplify that, yes? So what we do is we say, we can cancel out a pulling force with a pushing force because they're going to be equal because I've got a +1 and a -1, pulling and pushing. I've got another pulling force and another pushing force. So in essence, what we're doing is we're canceling out a core electron with a proton. And we're canceling out another core electron with a proton. What's the only thing we're left with now? If we've canceled out both core electrons and 2 of our protons, we're left with 1 proton only. Okay, so this is our 1 proton here. I'm going to color it in red. So we have 1 uncanceled proton. So if Q2 is our electron, what's Q1? It's our 1 uncanceled proton, yeah? But the amount of protons is going to be different. The amount of uncancelled protons is going to be different depending on the different elements, yes? So we need some other way of saying this. So this uncancelled proton is our Zeff. It is our effective nuclear charge. So it's almost as though this lithium has only one proton. It doesn't have any core electrons or any other protons. That's how it behaves anyway, okay? So if you recall, Z was the nuclear charge and it was the number of protons, right? Now we've canceled out some core electrons and some protons. So now all we have left is the only one uncancelled proton, and that is our effective nuclear charge. Is good? Okay. So we basically have our Q1. All right, so that's going to be what we compare when we're comparing with other atoms. Okay, so this is our Zeff. Just a reminder, if you're writing isotope notation, the number at the top is the mass number. Do you guys remember what that's equal to? That's the protons plus the neutrons. And we have our atomic number here. This is the number of protons. Z is nuclear charge. Now, S stands for shielding, and those are those repelling core, electrons. So the shielding is the repelling effect of the inner core electrons on the outer valence electrons. And they decrease the attraction felt by the valence electrons from the nuclear charge. This is an estimated number. So S is, there's a really complicated formula to actually figure out what S is, but we just use it as the number of core electrons. And that's going to be good enough for our purposes. Okay? Now, sometimes this is an aside. Do you know what it means when it's an aside? It's something you say over here. And it's not really that important. Okay? Because, take a look at this here, you are not responsible for explaining these two factors. That's why it's an aside. So if you actually don't want to pay any attention to me for the next 2 minutes, while I just briefly go over this, you can just be like, I don't want to pay attention. But sometimes people ask me things like, what about the repulsion between electrons in the same shell, right? I'm like, because that's not in my effective nuclear charge calculation, is it? No. So is there repulsion between electrons in the same shell? Yes, there is, but it is small compared to the repulsion from the inner electrons on the outer electrons. So yes, electrons in the same shell repel each other. But this repulsion is insignificant compared to the repulsion of the core electrons. Basically, what that comes down to is we can just ignore it, okay? So you don't have to ask about it, right? Because you'll be like, okay, I don't care about it because it's just really small. Now, there is another factor that actually, even better than just saying this is really small, let's ignore it. There is an opposing force as well that this causes a little bit of repulsion. This other factor causes a little bit of attraction, and they essentially cancel each other out. So this other factor, which you definitely do not need to be able to explain, but does have to do with nuclear penetration. We have the 1s here. We have the 2s here. And if you remember, the 1s actually looks like a sphere. And where is the density of that sphere? It is in the center. And as we move outward, it becomes less and less dense until we sort of hit a outside bit. Yes? Okay. Now, this is our 1s. Our 2s also has density right at the center. And it also kind of gets less as we move out. And then we have a node, and then we have more density. And now it gets really irritating to draw because there's so many dots and so much space. Yes? But the moral of the story is my nucleus is here. Yes? And my nucleus is here. And sometimes my 1s electrons might be further from the nucleus than my 2s electron. Yeah? Did that kind of make sense? So occasionally, that's why the Bohr model is not the best, because according to the Bohr model, this electron's always stuck here, but we know that it's not really stuck in this like spinny around the nucleus thing. It can sometimes get in closer, which will cause an extra attractive force. Do you care? Probably shouldn't. Okay. But it does explain why we can completely ignore the repulsion, because it is basically canceled out by this other attractive force. Okay? So here, Zeff, net positive charge. Caused by the combination of the attractive force of the nuclear charge and the repulsive force of the shielding electrons. The presence of the electrons on the inner shells reduces the effect of the nuclear charge, and that's why we call it the effective nuclear charge. And there it is, and that's it for that. And then there's some exercises, okay, which we will assign for homework. 10.1c, page 15. Here what we're going to do is we're going to look at the effective nuclear charge across a row. Okay, so this is across row 2. Okay, we're going that way. So we start with lithium, which we just did. It's got its 3 protons, so 3 things pulling in. It's got 2 electrons in its inner core, so it's got 2 things pushing out. We cancel all those out, cancel, 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 and we're left with 1 thing pulling in. So our Zeff is 3 minus 2 is plus 1. Is that okay? Okay. You looked a little stunned for a minute, so I just wanted to make sure it was all right. Now, beryllium. Beryllium has 4 protons. So it's got 1, 2, 3, 4 things pulling in, but we're adding the newest electron into the same shell. So how many core electrons do we have compared to lithium? We have the same. 2 core electrons here, 2 core electrons here. So we still have two pushes canceling two pulls. Cancel, 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 cancel. But now instead of having one pulling in thing, now we have two pulling in things. So our Zeff is +2. And we're going to just skip over all the rest because we didn't have room to put them all on the same page, over to fluorine. And unfortunately, I drew too many electrons on fluorine, so we're just going to get rid of this one. That's an oopsie. I need to fix that. Okay. Because fluorine should only have 7 electrons in its valence shell, not 8. You can get rid of them or not as you please, but we have 9 things pulling in. 1, 2, 3, 4, 5, 6, 7, 8, 9, but still only 2 core electrons pushing out. So how many things cancel? Only 2 of the pull-in things. And so we are left with 1, 2, 3, 4, 5, 6, 7 pulls in. And so our Zeff is +7. So which of the valence electrons are going to be pulled in tightest? Lithium or beryllium or fluorine? Fluorine's electrons are going to be pulled in tightest. So what's going to happen to atomic radius as we move across the period? It's going to get smaller and smaller and smaller because there's no new shells, but we're increasing the protons without increasing the shielding. Yeah? And we'll see that on the next page. We have a 5-step logical progression. The number of protons increases as we go across a period to the right. The added electrons go in the same energy level, so the shielding remains the same. However, protons increases, so Zeff increases. That means the electrons are pulled inward more strongly because Coulombic attraction is proportional to the charge. And what's the charge we're interested in here? Zeff. And so therefore we get a smaller radius. So as Zeff increases, that's essentially just increasing Q, because Zeff is the charge, Q is the charge, and Coulombic force is proportional to charge. So as we go across, this is our Q, 1 is our Zeff, the force gets bigger, so the Coulombic traction gets bigger. Now, you can use this 5-step process, or you can use whatever you want to compare the size of neutral atoms of sulfur and chlorine. Try to explain it using either the 5-step logical progression or some other reasonable method. Remember, when you're writing AP chemistry questions, nobody cares if you've written a beautiful paragraph. They just care if what you've written is correct. So point form is a big thumbs up, okay? So see if you can, maybe with your partner, maybe in a little group, write an explanation about what the sizes of sulfur and chlorine are compared to one another, and why. You good? Do you want? Yeah. This is just a possible. Do you know what I mean? But there's other ways of writing it too. And in fact, I have another one that I'm going to show you because everyone was like, can we not just do it using that logical 5-step progression? So I actually wrote one up on the logical 5-step progression. So we'll show you that one as well. So it doesn't matter if you use anywhere near the same words as I do, but you want to have those key concepts that they both have the same core electrons, right? But that chlorine has more protons. And so the Zeff of chlorine will be bigger than the Zeff of sulfur. And so whichever one has the greater Zeff will have the greater coulombic attraction for its outer electrons, which will pull them in tighter, which will make it smaller. So you're welcome to, like, you know, if you want me to, I can make a copy of that. But there's also, like I said, in response to people saying, how can I do this just using this? The number of protons increases as we go across a period. So basically, I just said number of protons in chlorine is bigger than the number of protons in sulfur. Yes, you could write it that way, and that doesn't take very many words and it doesn't take very much time. Yeah? And you could say the number of core electrons in sulfur and in S are the same. And then I like to show the calculation for the Zeff, 17 minus 10. You might even put, 17 here. 16, 10. 17 minus 10 is 7. 16 minus 10 is positive 6. And so therefore, the electrons are pulled inward more strongly in chlorine. Since Coulombic attraction is proportional to Zeff, and therefore chlorine has a smaller radius. But yeah, I would encourage you to work on just writing things without too much flowery stuff. You don't get any marks for pretty prose, okay? Just get to the bare bones of it. The other thing is if you write pretty prose, sometimes people make mistakes just trying to make their answers correct. Feel free to take a picture of it if you want to. I'm good with that. Or, you guys know how to find these notes on Teams? Yep. This is in period 2. So if you ever find something and you're like in our class and you're like, I don't know where it is, look in period 2 and maybe it's in that one. Okay. All right. Now, what happens to shielding and Zeff as we go to the next period? So what if we move from neon to sodium? So this is now on page 17. The last element in period 2, neon, has 10 protons and its core has 2 electrons. So the Zeff is 10 minus 2 is positive 8. Sodium, on the other hand, gosh, it's a lot bigger. Yes? Why is sodium so much bigger? We've only added 1 proton. Yes. It has a new shell, and we're not going to just say new shell. Every time we say shell, we're going to say occupied shell, okay? Because AP gets really wound up about that. They're like, everybody has all the same number of shells, blah, 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 blah. Anyway, whatever. It now has a new occupied shell, and every shell is bigger than the one before it, okay? So there's a lot of blah, blah, blah here, but the basic gist of it is Na has more occupied shells than neon. And each subsequent shell, do you guys know the word subsequent? It kind of means like the next one, okay? But you can't say each the next one because that sounds weird, okay? So it's a helpful word to learn. Each one in turn, you could say, and you could say each shell in turn being larger than the last one. Each subsequent shell being larger than the previous. But that's not all. What is the Zeff for sodium? We have 11 protons, and we have 2 plus 2 plus 6 is, why does it say 8 core shielding electrons? That should say 10. Fix. Core shielding electrons. And we get plus 1. So not only does it have more occupied shells, but also it has a smaller attractive force on its outer electrons because the Zeff is smaller. So basically more shells, less pulling, okay? More shells and less pulling. Therefore bigger. Okay, now let's take a look at what happens as we go down a single group. So now, if you remember, what do you know about the Zeff for all the elements in a single group? They are all the same, okay? So here we have our Z. So our protons, this is our nuclear charge, is 3 for lithium and 11 for sodium. Our core electrons, though, also go up. So we go from having, 2 core electrons to having 10 core electrons. What's the difference between 11 and 3? 8, yes? What's the difference between 10 and 2? 8. So we've increased the protons, but we have increased the shielding electrons by the same amount, okay? And that's why the effective nuclear charge stays the same. And then I think I got a little carried away with the diagrams. So we'll see. We might have to skip some pages here. So here's our valence electrons. 1 valence electron here, 1 valence electron in sodium. More occupied shell, therefore the atomic radius is bigger. Now let's look at Zeff. Here is lithium. Its Zeff is +1. You could go through and cancel all these out, and in fact, I think I do on the next page. Anywho, ignoring them, you can see all of them cancel out, cancel, and you are left with one thing pulling in. Okay, so you've got the same effective nuclear charge. So the Zeff is +1, the Zeff is +1, and if we were to do the exact same thing for potassium, the Zeff would be +1. So what effect does Zeff have on the size of the atom as we go down? Anyone? Yes. Yeah, absolutely. It stays the same, so it has no effect, right? Okie dokie? So if you're explaining atomic radius going down a group, you can ignore Zeff. You don't explain in terms of Zeff. You explain in terms of number of shells, right? Because that's what's changing. As you go across a period, how does the number of shells affect the size as you go across a period? How does the number of shells affect the size? What happens to the number of shells as you go across? It stays the same. So how does shells affect as you go across a period? It doesn't. Okay, so when you're going across, you explain atomic radius in terms of the effective nuclear charge. When you're going down, you explain it in terms of atomic radius, in terms of number of shells, occupied shells. Number of occupied shells, I have to use that word too. So as we go down a group, the primary factor is the occupied shells. Watch your language. The College Board does not want to hear that Na has 3 shells. It wants to hear that Na has 3 occupied shells. Okay? So if we were asked who has a larger atomic radius, O or S, you would say O has 2 occupied energy levels. S has 3 occupied energy levels. Each subsequent energy level is further from the nucleus. Therefore, S will have a larger atomic radius than O. And I believe that you can just stop right here. The AP exam does not go in for big, long, wordy explanations too much, okay? Very often they only want like a little thing. And I think they give you boxes now that kind of like hint at how much you should be writing. It used to be you just got like lined paper and you got to write, but I don't know how they do it now. But usually the questions, like each little single part of a question is worth 1 or 2 marks. Right? There's part A, B, C, D, E, F, and usually each one is only worth 1 or 2 marks. So they probably don't need you to go on and on and on. Yeah? Okay. You could, if you wanted to, if you had extra time at the end and you really wanted to be sure, you could also say, as I go down a group, the effective nuclear charge does not change much. You know, and you could compare the Zeffs of the 2 of them, and so that will not have an effect on the size. But you've been asked to explain why the size change is not something that doesn't affect the size. So, do you know what I mean? Okay, cool. Summary. You can read that if you want to. There's some exercises. Let's go to 10.1D, page 24. So there are 4 main periodic properties. The first one is atomic radius, which we have just talked about. And how do we define atomic radius? It is the size of an atom. And how do they define that size? It is half the distance between 2 nuclei bonded together. I don't know why they chose that one. There is some reason. I've read it several times and it just does not stick in my mind, so it's not obviously too important. I think the gist of it is that if you have a hydrogen bonded to a hydrogen, right, they kind of make this shape, right? And so the radius is this radius. It would not be the radius of the atom. But I don't think that matters, and I don't know why that line went beyond the circle. Honestly, I don't think it's important to the course. Okay, so we're just going to skip over that, and we're just going to say atomic radius, you know, like a radius. Electronegativity, we've already talked about electronegativity, so hopefully this should be a little bit reviewy, if not completely. Electronegativity is the ability to pull bonding electrons towards itself. Okay? So it's all to do with bonding. Ionization energy is the amount of energy required to remove a valence electron from a gaseous neutral atom. So I don't care if we're talking calcium or fluorine or gold, you're going to have a single atom and it's going to be a gas. They did that so that you can compare the ionization energies of all the things. Because if you have one that's in the solid state, like bonded to a whole bunch of other metals, it's going to behave differently than, say, diatomic chlorine, right? So in order to have things to compare, they used, and obviously they would have to create these gaseous atoms somehow. They would have to heat, say, metal really hot so it gave off some gas and then throw some ionization energy at it. And those physicists, man, they got like lots of mad skills. So I don't know. I don't know how they do it all, but anyway, gaseous neutral atom. And that's going to be an endothermic process, because if you want to rip it away from its nucleus, that requires an input of energy. It's not going to come off all by itself. Okay, and nobody's literally going in there and using their hand to rip it off. What do we use to get electrons out of atoms? Photons. So you actually know a little bit about ionization energy already, because the PES, the photoelectron spectroscopy, was all about ionization energy. Okay? And just to be a little bit more specific, this is the first ionization energy. The second ionization energy would be taking off a second electron. So you'd be going from a +1 ion to a +2 ion. But if we say ionization energy and we don't specify, we usually mean first ionization energy. So you can just make that assumption. If we want to say second ionization energy, we will use the term second. Electron affinity is kind of like the opposite. We still are taking a gaseous neutral atom, but instead of ripping an electron off of it, what are we doing here? We're adding an electron to it. Do electrons like to be close to nucleuses, or do they like to be far from nucleuses? They like to be close. So in general, if you take an electron and you bring it in and allow it to go into whatever shell is the closest to the nucleus that's still got an empty spot in it, it's going to release some energy. Okay? So these are going to be kilojoules here. This is going to be kilojoules here. So this is an exothermic process. So we've already talked about atomic radius. So you can just see the little pictures here that makes it really graphic for you. You can see helium is teeny tiny, okay, and rubidium is big and fat, okay? So tell your partner, why do they get smaller going across a row? They get smaller due to the increase in protons, which therefore leads to an increase in Zeff, which leads to an increase in Coulombic attraction. Is good? Okay. Why does the size get bigger as you go down? More occupied shells. Good. We've got one periodic property under our belts. Excellent. Good job. Give yourself a pat on the back. Electronegativity. You have to have a bond to be looking at electronegativity. There's no such thing as the electronegativity of an atom in isolation, because it is literally the ability of an atom to pull bonding electrons towards itself. So it affects the electron distribution within a bond. So if we have methanol here, we have an O and an H. The O is more electronegative. The H is less electronegative. And so we have a greater electron density around the oxygen and less electron density around the hydrogen. And we would end up with a dipole. Which way would the dipole point? Towards the oxygen. Okay, that's our dipole. And this would be a polar molecule. You would also end up with a bit of a dipole here as well. And so it would kind of all point towards the O. Okay? But this would be bent, so it... Forget I said anything. Just whatever. We'll just talk about that one bond polarity. All right, and here's our little picture of electronegativities. They are approximate because you cannot measure them directly. They have to be calculated from other properties. And I don't know why gold is higher, but the main thing is that they get really big over at fluorine. And why are they big over at fluorine? Fluorine is both small and if it is small, what can you say about R? And what do I mean by R? The radius. Remember, Coulombic attraction is equal to K, Q, Q over R squared. F is small, therefore R is small. Therefore, Coulombic attraction is big. That's one factor. But what else can we say about fluorine that affects the Coulombic attraction? That's one thing we can say about fluorine. Fluorine has a large What's the other thing that affects Coulombic attraction? R affects Coulombic attraction. What else affects it? Whoa, what happened? Okay. Zeff. Right? Why will you not let me grab my blue pen? Oh, okay. Control Z. Okay. Control Z. There we go. Okay. Okay, here we go. This Usually what we're talking about is Zeff here. Yeah. I mean, we could call it Q2. It doesn't matter which one you call it. Yes. F has a large Zeff. And therefore, Q is big. And therefore, FC is big. So we've got both the atomic radius and the Zeff causing the Coulombic attraction to be big. Yes? And as we go from left to right across the periodic table, Zeff gets bigger. So the Coulombic attraction gets bigger. So the electronegativity gets bigger. As we go across the periodic table, the atom gets smaller. So the radius gets smaller. So the Coulombic attraction gets bigger. And so the electronegativity gets bigger because everything, all of the periodic properties all come back to Coulombic attraction. The bigger the Coulombic attraction, the more extreme the property. Now, electronegativities, we have differences in electronegativity 0 to 0.4. That is nonpolar, so we have a small difference. And you can see, oh, stop. Stop making, Jesus. Good Lord. Okay, there we go. Small difference, you end up with a nonpolar bond. Medium difference, we end up with a polar covalent bond. And you'll notice, oh, look at this. We got a couple numbers there that separate the big difference from the medium difference. And that's because this is a continuum, right? These divisions are arbitrary. Yes? And chances are you're not really going to ever have to look at some electronegativity values and tell us whether a bond is polar covalent, or ionic. Okay? You should know that metals and nonmetals make ionic bonds, even though if you were to take copper and put it together with iodide, you would have a difference of 0.6, which is clearly just barely in the polar covalent category according to this. So don't get too excited about those values and the differences, okay? Just know your general things and know FONCH. Do you know your FONCH? Okay, F is bigger than, O is bigger than, N is bigger, or no, is F? Yeah. F is greater than, O is greater than, N is greater than, C, which is approximately the same as H. And that's really all you need to know about, okay? Other than the fact that if you have something which is higher on the periodic table, it is more electronegative. If you have something that is lower on the periodic table, it is less electronegative. So, most electronegative, least electronegative. Ionization energy. We already talked about it being from a gaseous neutral atom, and this being our first ionization energy. And what takes it out? A photon. And let's look at our colors here. Where is our highest ionization energy? Helium. Highest ionization energy. And what else is happening up in that top right corner? What's the coulombic attraction like in that upper right corner? Is it big or is it small? Yeah, this is our biggest coulombic attraction. I'm just going to call it FC because I don't want to write too much, okay? Our lowest ionization energy is down here, and that's because it has the smallest coulombic, FC. If you have a high coulombic attraction, it's going to require a lot of energy, to kick out an electron. If you have only a small coulombic attraction, it's only going to require a small amount of energy to kick out an electron. Did you notice that the ionization energy trend and the electronegativity trend are the same? Because they both depend on the biggest or smallest amount of coulombic attraction. And guess what? Electron affinity? Basically kind of the same thing again. Okay, because what's it doing? What are we doing here? We're grabbing an electron and we're saying how much energy is released. Now, I don't like electron affinity because some books give it a positive value and some books give it a negative value, and that irritates me because I don't like inconsistency. But basically, if you see a bigger number, that means you're releasing more energy, regardless of whether they give it to you as a negative, which obviously implies that it's released, or whether they give it to you as a positive, and then you just have to say it's released. Bigger number means it releases more energy. Bigger number releases more energy. And think about it this way. If you have something that's not very attractive, right, down here, this is not very attractive. FC is small. Not so attractive to electrons. Are you going to release more energy or less energy? Less. But up here, coulombic attraction is big, so we release more energy when we grab an electron. And your homework is pages 13, 14, 23, 27, 28, and half of the reviews. Okay? Big Chem weekend. Sorry, that's life. More.